We're going to begin looking at breathing. Breathing is dependent on gas pressure. Pressure and volume are inverse functions of one another. So as far as we're going to look for today, as the pressure rises, the volume will decrease and vice versa. Gases are always going to flow from an area of high concentration to an area of low concentration, or from an area of high pressure to an area of low pressure. The first part of breathing is inspiration. To begin inspiration, the muscle called the diaphragm is going to contract. When the diaphragm contracts, it goes from being a dome-shaped to a relatively flat-shaped muscle. Additionally, what we call the intercostal muscles are going to contract. Intercostal muscles are those that are located between each rib, so they're also going to help pull the rib cage out. By doing that, we increase the volume of the thoracic cavity. So again, take this into consideration. As the diaphragm moves down, do you see how the volume inside the thoracic cavity would increase? Is on the same hand as the ribs kind of move up and out, the volume increases again in the thoracic cavity. You can get a good idea of how the ribs work, or the intercostal muscles, by putting your hands on the side of your rib cage and taking in a deep breath. They kind of act as they call it a bucket handle motion, as though you're pulling the side of a bucket handle up. Regardless, you're increasing the volume of the thoracic cavity. As we mentioned before, as you increase the volume, you decrease the pressure. So the pressure in the lungs is going to fall slightly below atmospheric pressure. Now we've got a pressure gradient. As a result, the air is going to move from a high pressure outside in the atmosphere to a low pressure inside the lungs. As a result, you inhale. Expiration, on the other hand, is a completely passive process because the two muscles that we spoke about, the intercostals and the diaphragm, are going to relax. When that diaphragm relaxes, again, it goes from being a relatively flat muscle to being dome-shaped. And as a result, it pushes up on the lungs. That will decrease the volume inside of the lungs and force the air out. So literally, just by relaxing the muscle and then having the elastic recoil, say of the abdominal muscles that you had squished when you contract the diaphragm, both of those will push up on the lungs and the pressure will increase. As a result, the volume inside the lungs decreases and you exhale. Taking a look at this picture, you can see really well the diaphragm just underneath the rib cage, how it's that dome-shaped muscle. And then in number 2, they have the arrows pointing that this muscle is going to come down. When it does that, it increases the volume inside the thoracic cavity, decreases the pressure, and air rushes in. Number 3 then is just the opposite. The diaphragm moves back up, and the volume is going to decrease, the pressure will increase, and you will exhale. All of that, of course, is passive. Now, there are different volumes and or capacities inside of the lungs. The first volume that we're going to look at is something called tidal volume. So like the tides of the ocean come in and out and in and out, tidal volume is simply your normal breathing rate. So it's your volume of air that's inhaled and exhaled during normal breathing. You probably recognize that you can inhale much more and you can exhale much more than you do under normal circumstances. So the normal situation is a tidal volume. We can also talk about dead volume space, and that would simply be areas of the lungs that you could put air into but maybe aren't using at the time. So volume of air in space is not exchanging gases. The vital capacity now is going to be the volume of air that can be maximally inhaled and then maximally exhaled, or the volume of air that you can physically move into or out of your lungs, taking the deepest breath possibly and then exhaling the deepest breath possible. There's a volume called the inspiratory reserve volume. This is going to be the volume above and beyond the tidal volume that you can inhale. So the volume of air that can be inhaled in addition to the tidal volume. So you normally are breathing, you don't inhale as much as you possibly can, but that would be then the inspiratory reserve volume. Taking a look at this picture, we've got a green kind of squiggly line moving back and forth and back and forth. That would be your tidal volume. And then as it peaks up to about 6,000 milliliters, that's going to be your inspiratory reserve volume. But as we move from the inspiratory reserve volume, the deepest breath that we can possibly take, and then you can see the deepest breath exhaled as that moves back down to just over 1,000 milliliters, that's going to be your vital capacity. There's also an expiratory reserve volume. The expiratory reserve volume is the volume of air that can be exhaled in addition to the tidal volume. So clearly when you breathe, under normal circumstances, you are not forcing all of the air out of your lungs that you could. As a result, if you forced that extra air out, you would be using up the expiratory reserve volume. Now, there's always going to be something called a residual volume inside of the lungs. This is the amount of air that remains in the lungs at all times. Think about this for a second. If you were able to forcefully exhale all the air out of your lungs would collapse. Therefore, this residual volume is a volume of air that you cannot force out of your lungs. And if we wanted to measure any of these volumes, we would use a spirometer. That's the instrument used to measure the different lung volumes. And if you have asthma or know somebody who has asthma, they probably have used a spirometer in a doctor's office so that they could see where the volumes were at and what the problems with respiration were. Taking a look again, you can see that anything in the blue line below is the expiratory reserve volume, and then anything in the pinkish color at the very bottom is that residual volume. That's the volume that, regardless of how hard you try, you cannot move out of the lungs. Now, the reason that gases diffuse is due to a partial pressure gradient. So the partial pressure of a gas is equal to the percentage of the total gas composition. What you are breathing right now, the air, is not 100% oxygen. Gases, again, are going to diffuse down that partial pressure gradient. So they're going to move from an area of high partial pressure to an area of low partial pressure. Atmospheric pressure, under normal circumstances, is 760 millimeters of mercury. Nitrogen makes up 78% of what you're breathing in the air. Oxygen only makes up about 21% of what you're breathing in the air. And then carbon dioxide is 0.04%. The rest of it is insignificant numbers of other gases. So then less than 1% of all other gases combined. So we need to calculate the partial pressure, let's say, of oxygen. We said it was equal to the percentage of the gas composition. So we would take 760, because that's the total of the composition of the gas, so 760 millimeters of mercury, times 0.21. I got the 0.21 because that is the decimal form of 21%. Multiply those two together and we get 160 millimeters of mercury. So that would be the partial pressure of oxygen. We could do the same thing for nitrogen or the same thing for carbon dioxide. Now, taking a look at this picture, you can see the external respiration, at least, on the right. They've taken apart and blown that up. So you see that there's an alveolus, and inside the alveolus, the partial pressure of oxygen is 104 millimeters of mercury. And inside the capillary, it's 100 millimeters of mercury. Therefore, you can see that the oxygen is going to diffuse from an area of high partial pressure inside the alveolus at 104 millimeters of mercury to an area of low pressure inside the capillary at 100 millimeters of mercury. We can also see the carbon dioxide on this. You can have a partial pressure of carbon dioxide at 46 millimeters of mercury inside the capillary and a partial pressure of carbon dioxide at 40 millimeters of mercury inside the alveolus. As a result, we're going to move from an area of high partial pressure inside the capillary to an area of low partial pressure inside the alveolus, at which point we could exhale that CO2 then. This picture is similar to what we saw before. And again, if you take a look at the bottom now for internal respiration, you can see that we're going to be moving gases between the bloodstream and the tissues of the body. So we would have, for oxygen, a partial pressure of 100 millimeters of mercury inside the capillary and about 40-ish or below, let's say, inside the tissues. Now, that would cause our oxygen to move from an area of high partial pressure inside the capillary to an area of low partial pressure inside the tissue, giving that oxygen up to the tissue. Carbon dioxide, now we know that the cells are metabolically active. They produce carbon dioxide as a waste product of cellular respiration. We need to get that out of the body, and by doing so, we've got a partial pressure of greater than 46 millimeters of mercury inside the tissue and about 46 millimeters of mercury inside the bloodstream. Therefore, we're going to move from an area of high partial pressure inside the tissue to an area of low partial pressure inside the bloodstream, getting that carbon dioxide into the bloodstream where we can carry it back to the alveolus. Regardless, the idea here is just to show you that gases always diffuse down this partial pressure gradient. So if you know what the partial pressure of a gas is in any particular part of the body, you can determine where it's going to move to.